Start of a new chapter here in our trig class. This is the beginning of the miscellaneous chapter. Some nice things. We start off with little polar coordinates. Introduction. So the story goes like this. A long time ago there was a guy named Descartes, the French guy, 17th century guy, 16 something, Descartes. He was a philosopher, mathematician, scientist. Back then people did everything. There was no problem. As he is credited with the invention of the famous Cartesian system, which is the one you're used to, the one we've been doing all along. The Cartesian coordinate system is a way of naming points on the plane to figure out where you're at. For example, every single point here has a special name. If you wanted to indicate that point right there, you'd say, hey, you start off from some middle point here called the origin, and what you do is you go 1, 2, 3, 4, 5 units to the right, and 1, 2, 3, 4 units up. And so this is called 5, 4. That's the name of that point. This is called an ordered pair. The order does matter. The first one tells you how many units to go left and right on the x-axis, and the second one tells you how many to go up and down on the y-axis. That's what you're used to. -1, -2, -3, -1. That would be this point right here. -3, -1. Famous Cartesian system. Famous guy Descartes invented the Cartesian system. Right around the same time there was an adversary who had a different point of view. This other person said, you know what, that's not the only way to figure out where you're at. You just don't always have to go left and right and up and down however many units. There are other ways to name the points. So this adversary came up with a different possibility. The adversary was called is an Italian guy by the name of Pinocchio, and Pinocchio had this idea, you know what, it doesn't have to be that way. We could, instead of having straight lines that's too straight up and down and left and right, we could have curvy lines like this. We could have concentric circles. And here's the way we do it. You name, first of all, you recognize and you mark the angles the way we've been doing it, standard notation and standard angles, standard position. So we call this one 0 degrees. We call this one, we go for positive angles, we go clockwise. So this would be 30 degrees, this would be 60 degrees, this would be 90 degrees, and this would be 120, etc., etc., 180, etc., etc. And this would be negative angles. For example, -30 degrees, -60 degrees, negative this way, positive up, so on and so forth. In fact, some of these overlap. -30 degrees points in the same direction as positive 330 degrees. And we talked about this before. So Pinocchio had this idea, hey, we could use this as a coordinate system. It's easy. All you do is first you say which way you're pointing. You point in the right direction, and then you move forward that many units, or actually backwards that many units. And so that's why Pinocchio is the perfect person to invent the system, because Pinocchio's got a really big nose, and all he has to do is point the nose in the right direction and then travel in that direction. Let me give you an example. So we take the top view of Pinocchio, that's this view, and we put him here. Let's say we put him starting off in standard position, right? So he's pointing at the 0 degrees direction, 0 degrees. And suppose we wanted to plot the point, let's say let's plot the point 5, 60 degrees. This is the way we will have the ordered coordinates, ordered pairs in polar coordinates. The first one tells you how far to go, and the second one tells you in which direction. And it's actually, this is a simplified statement, because really, if the 5 is negative, it also tells you the direction. The direction would be -5 units walking backwards. So for example, let's do this one, 5 and 60 degrees. 5, 60 degrees. Here's what you do. You first point in the 60 degrees direction. So you go, that's 30 degrees. That's not where we want to go. Spin some more. That's 60 degrees. That's exactly, well, that's exactly pointing in the right direction now. 60 degrees. This is 60 degrees. And once you're pointing in the right direction, then you just travel 5 units. So you go 1, 2, 3, 4, 5. There's your spot right there. So this spot right here, that spot right there, 1, 2, 3, 4, 5, that's called 5, 60 degrees. And so this is the alternative view to Descartes' straightforward world, left and right and perpendicular lines. Pinocchio has this alternative way of looking at it. First, point in the right direction, and then move in that direction. Let's practice that a little bit. Again, let's try to practice plotting 4, 120 degrees. So here's what you do. You first look in the 120 degrees direction. So you start off at 0, then you go that's 30 degrees. Then you're looking at the 60 degrees direction, and then you're looking at the 90 degrees direction. You got to go some more. You're looking at from 90, how much more have you got to go? Each of these pieces, see, if this is 0 and that's 90 and I've cut it into 3 pieces, each of these is worth 30 degrees. Same for these, each of these is worth 30 degrees. So from 90 degrees, the next 30 would be 120 degrees. Next one would be 150, and we would end up at the expected 180 degrees, and so on and so forth. Anyways, once you're pointing in the 120 degrees direction, you've got to go 4 units forward. So you'd go 1, 2, 3, 4 units that way. So this would mark the spot right here. 1, 2, 3, 4. That marks the spot. That point right there is 4, 120 degrees. Get it? That was so fun. You guys want to practice again? To practice again, you reset Pinocchio back at looking at the origin, and then you try something. Say something like this. Let's try something in blue. How about if you try 3, negative 150 degrees. Take that. So the first thing you do is you look at the negative 150 degrees direction. This would be negative 30, 60, negative 90, negative 120, negative 150. That would put you over on this spot, negative 150. So you get your Pinocchio starts looking in the right direction. Now he's facing the right direction, and now he has to travel 3 units. So he goes 1, 2, 3 units, and there it is. That's the spot right there. I'll move him to mark the spot. 1, 2, 3. That's the spot right there for the blue point. You get it? It's real easy. All you do is point in the right direction. That's why he needs a long nose, so he can point in the right direction, and then just move forward or backwards. Let's try a backward one. Actually, you know what? Descartes had the nose for it. He would have done well with polar coordinates as well. Alright, let's try a negative one. Let's try, how about 180 degrees, and we'll try negative 2. Negative 2, 180 degrees. Alright, we can do it. So the first thing you do is you look in the right direction. 180 degrees, that would be this way. That's looking at 180 degrees. Looking that way, 180 degrees. Now, this is the first one we ever do that's negative 2. If it was a positive 2, Pinocchio would move forward to 1, 2, and that would be the spot right there. If it's a negative 2, then you got to walk backwards. So you walk 1, 2, and that's the spot. That's the spot right there. Right here. This is the spot for negative 2, 180. Negative 2, 180 degrees. See that? Alright, that's the basics of plotting points. The one thing that it needs to be pointed out immediately is the fact that unlike reset them at origin. By the way, in polar coordinates, the origin is called the pole. By the way, now the important thing that needs to be emphasized is that unlike the world of Descartes, where every single point has a unique name, I mean, you could call this something else. You could call this 5, 8 divided by 2, but these two numbers are equivalent. Really, there's no other way to name this point. It's 5 and 4, 5, 4. Every single point has a unique spot. Every single spot has a unique point, or unique name, the ordered pairs. That's not the case for polar coordinates. Watch this. What if I ask you to plot, let's do a different color now, let's do green. What if I ask you to do 2, 360 degrees? Where would that be? 2, 360. Think about it. First, I take Pinocchio and I have him face the right direction. He's got to face the 360 direction. So he goes 30, 60, 90, 180, 270, 360. Well, okay, now he's facing the right direction. Now he's got to move 2 units forward. 1, 2. Where does he end up? He ends up in exactly the same spot as the -2, 180. Right? So this spot right here is also has, besides having one name here, it has, you could call it -2, 180. You could also call it 2, 360. So right away you see 2 different names for the same point. That doesn't happen in Cartesian plane. It happens a lot in polar coordinates. In fact, every single point has infinite many names, because you could also call it, I could also call it 2, 0 degrees, right? Or I could also call it 180 plus 360, that would be 540. 540 degrees direction. 540 degrees direction. That would be facing that way, and I could go -2. There's another name for it. 1, 2, 3. I already give you 4 different names for the same spot. And really, there are infinite many. This one, for example, we could create another name. We could say, have Pinocchio face. Let's see. We'll have him face this way. We'll have him face that way. And once he's facing that way, we'll have him walk backwards. 1, 2, 3, 4. See how easy that is? So, let's see. This direction is 1, 2. This would be -60 degrees. We'll have him work backwards. 1, 2, 3, 4. So, -4, 60 degrees would be an alternative name for exactly the same spot as 4, 120 degrees. Told you. Every single point on the polar plane has infinite many names, and by names I mean ordered pairs. That doesn't happen in the world of Descartes. This guy, every single point, he's only got one name for it. In this world, every single point has infinite many possible names, because you could spin any which way. You could spin 5 times and then end up at that direction, etc., etc. Now, the next question is, well, why in the world would you go through the trouble of inventing polar coordinates? Well, it turns out that you could think about these as 2 separate worlds. You got the Cartesian world and you've got the polar world, and some problems become incredibly complicated in this world and incredibly easy in this world, and vice versa. So sometimes it's good to have both worlds. And not only that, but it's good possibly to build a bridge, maybe build a happy bridge between the 2 worlds, so that problems and questions in this world could be translated using the bridge into the other world, and vice versa. And that's really the ideal situation. If you can, this just adds more tools to your toolbox. Instead of looking at a problem in Cartesian world, you could look at it in polar world. That's the point. So that leads me to my next point is, we want to be good at translating points here to points there. That's got to be a high priority for us. Being able to translate from polar language to Cartesian and vice versa. Okay, so let's translate our first point. This is in polar coordinates 5, 40 degrees. And the question is, how do we translate that to Cartesian? Well, fortunately, there's nothing to this. We already have all the tools to do this. What we do is we make a triangle out of it. In fact, we make a right triangle out of it. And in doing so, we turn this into a problem where we solve the triangle, because this is your x and this is your y. If you could just solve for x and y, you'd be in business. And we had this huge chapter on solving triangles. If you know certain things on 3 of the 6 items, you can solve the triangle. Here we know 3 of the 6. We know that this is 5. We know that this is 40 degrees, and we know that this is 90 degrees. Those are 3 items. The rest is easy. Here's what you do. The ratio of opposite to hypotenuse is given by sine. So all you'd have to do here is multiply by sine of 40 degrees. The ratio of adjacent to hypotenuse is cosine. So all you'd have to do is multiply by cosine of 40 degrees. And so you'd get that x is equal to 5 times cosine 40 degrees. And y is equal to 5 times sine of 40 degrees. So there it is. If you wanted to translate that, this is exactly how you translate it. In fact, if you could get a little magic number machine, clear everything. You go 5 times sine of 40 degrees is approximately 3.21. So y is approximately 3.21, and this is approximately. So we clear everything and we go like this. We go 5 times cosine of 40 degrees. What is that equal to? About 3.83. 3.83. So this is, when you translate it, becomes approximately 3.83 comma 3.21, and this would be in Cartesian. I told you. Not only that, but what we should get out of this, something really important, not just the translation of this particular point, but the general translation. By the way, this would work in any quadrant. This is good forever. But let me generalize it for us. Let's generalize it here. Here's the bridge. I'm not too happy with the happy faces. I'll just draw a regular bridge. So every time you've got a point here, and this is r and this is theta, this is incredibly important. You can immediately get to the x's and y's. Here's how you do it. X will be equal to r times cosine theta, and y will be equal to r times sine theta. I can't emphasize how important this is. We will come back to this over and over again. We'll come back to it when we convert into Euler forms. The Euler form of a number. Huge topic coming up. Anyways, this is your dictionary to go from polar over to Cartesian. The point will be r times cosine theta, comma r times sine theta. Okay, that's how you translate. Now, every good dictionary, foreign language dictionary, has 2 parts to it. It has the translation when you go that way, say from English to Russian, and then it has a translation as you go back from Russian to English. So what we'd like to do here is supply the other half of the dictionary. How do you go backwards? If you have x and y, how do you find r and theta? Okay. Take any old point here in the Cartesian plane, like 5 over comma 2, and let's convert it to the Pinocchio world, to the polar coordinates, for fun. Really, there's nothing that you need. You just need common sense. But perhaps I should point out some little subtleties here. Remember one of the most crucial differences between the Descartes world and the polar world. What was one of the crucial differences? One of the crucial differences is that in here, every point has infinite many names. In this world, every point has exactly one name. So, if you were to take a point here and translate it to the XY world, there would only be one place to go because every point has exactly one name. But if you were to go backwards, every point has infinite many names. So this point right here has infinite many names. So when you go backwards, there may be infinite many choices for you to name that point. The angle could be, for example, if it was 45 degrees, it could be 45, or negative 315, or 45 or 4 or 5. There are so many choices, infinite many. So the translation that way is a little bit ambiguous, I would say, because there could be many different right choices. Let's try it and see how it goes. Okay, so again, if somebody was two different reasonable people were to translate this, they might get reasonably correct different answers. Okay, so let's do it. First thing you note is that, hey, you know that the 5-2 means that if you have a right triangle, well, the 5 is telling you that you've gone 5 over from the origin. In polar coordinates, you call this the pole. In Cartesian, you call it the origin. This 5 is telling you that distance is 5 and this distance is 2. Well, again, how many pieces of the triangle do you know? 1, 2, 3. So if you can find the other ones, then you're in good shape. You need to find the theta and the r. That's all I really need to write in polar coordinates. You don't even need the other angle. If I can find theta and r, we're in good business. We're in good shape. And we've already become experts at solving triangles, so really there's nothing new that I could tell you that I haven't told you before that would help you solve this. You should be able to solve for r and theta using the ideas we already know. But just for fun, let's practice those ideas. Here, we know that tangent theta would describe the ratio of opposite to adjacent. So already there, that will give you the theta. Well, I'll say more about that in a second. How about r? We could find r so many different ways by finding the ratios. Once we find theta, we can also solve it this way. Two of the sides are known on the right triangle. Every time you know 2 of the sides, and you want to find the third one, what time is it? It's Pythagoras time. So we could say by Pythagoras, r squared is equal to 2 squared plus 5 squared. And using these 2 equations, you can solve for r and theta. Okay, that's all you need. But let's do it carefully. So r squared is equal to 25 plus 4 is 29. So r is equal to plus or minus the square root of 29. Now let's think about this carefully. Which one is it, the positive or the negative? The answer is it could be both, the positive r or negative r. Because maybe Pinocchio, let's take our little copy of Pinocchio. Where's Pinocchio? Where are you, buddy? Let's clone you. Here you go. Here's something fun for you to try. Which r is it? If Pinocchio is facing that way already, then of course he'd have to walk in the positive r direction. But suppose that Pinocchio is facing the direction that's exactly 180 degrees from that, then he would be walking backwards. So r could be positive or negative depending on your choice of theta. Got it? Next, which is the right theta? Well, we learned how to solve these equations a long time ago, back when we were, I don't know, it was chapter 4, I believe. This is a basic equation. The way we solve these is by drawing a graph of the sine curve, or no, of the cosine curve. You draw the 2/5, that's run here, and you point at the solutions. How many solutions have you got? Well, really, you have infinite many solutions. I told you there are many possibilities for theta. You can't really say which one it is. The calculator will always give you the one between 90 and negative 90. In fact, let's see. If I do that tangent, let's do a little shift. No, let's clear everything. Shift tangent 2 divided by 5 is equal to about 21 degrees, 21.9. So this is 21.9 degrees that only gives you one of them. There are infinite many choices. You know what, I'm going to choose this one. What would that one be? Well, 120 or 21.9 plus 180. That would be 201.9 degrees. And so on and so forth. So here's the conclusion here. You could call this point, you know this is 21.9 degrees. So you could call this point square root of 29, comma, 21.9 degrees, and that would be perfectly reasonable. However, my point is that somebody else who is also reasonable could say, you know what, maybe the angle is this one, maybe it's 201.9 degrees. That's where Pinocchio is facing as he is now. He's facing more than 180, he's facing the 201.9 degrees direction. And once he's facing that way, he's going to walk backwards, negative square root of 29. And that would be perfectly reasonable as well. There are infinite many ways to translate. Both of these are good. You know, there's not one best answer per se. You just have to look at the picture and make sure you coordinate the right r with the right theta. And that's about it. By the way, we've never ever had a triangle with a negative hypotenuse up until this point. The r could be possibly negative square root of 30 or 29. Interesting, huh? I know, huh? Anyways, that's how you translate. And what we could take from this, from this specific example is the fact that that to get theta you could play, to get r you could play this game. R squared is equal to x squared plus y squared. That came from Pythagoras. From here, r squared will always be x squared plus y squared. The other thing we can take from this is that tangent of theta is equal to y over x. Okay, so long as x is not 0. And this could help you translate. You see, r is not really solved for because there are many choices for r, and theta is not solved for because there are many choices for theta. So you have to resolve each one on an individual basis, on a problem-by-problem basis. And that's inherent in the way the situation is, because in this world, every point has a unique name, and in this world, every point has infinite many names. So there's no way of getting around that. Really, there are infinite many ways to go there. The best you could do is just write down the equations. This will certainly always be true, at least so long as the bottom here is not 0. Okay. I think that was sweet. That helps you do simple things. That helps you, introduces you to polar coordinates, helps you plot points, and helps you convert from this world to that world and back the other way. What we got to do next is maybe study some graphs in polar coordinates. But that could wait for another day. I think today we did good.